All right. So, my favorite class in high school is actually European history. Uh, uh, European history. Really, it was my favorite class. Even though I got a 2 on AP exam. Huh? All right. So let's talk about introduction of calculus. Shh. Josiah, shut up. I wish I had a button. Just had to press. Josiah, shut up. Josiah, shut up. It'd be like I need to buy. What's that thing called? Like the control, like the soundboard. Yeah. Josiah, shut up. Josiah, shut up. Oh, you're gonna give me one? Oh, okay, okay. I need like a pre-designed button. Josiah, shut up. All right. So let's talk about introduction of calculus. So let's start. Who invented calculus? Does anybody know who invented calculus? What? Sir Isaac Newton. You are right. No, there's no way. I'm too dumb for calculus. All right. Shh. So who invented calculus? And the first person is everybody know Isaac Newton. But you know, on sports, right? Nobody remembers second place, right? So there's actually another person. And the second person is I don't I I think you guys can look it up. This name is Gottfried Leibniz. Gottfried Leibniz. Um. So uh, Leibniz. Sorry, how Leibniz. Hold on. Shh. I just want to make sure I spelled it correct. Oh, sorry, it's not. I spelled it wrong. Sorry. Let me respell this. So Gottfried Limbus. Okay. You should know the history of things because if you are in happen to have a math major, you are gonna have to study mathematics for history, history of mathematics. So they will talk about all those people contributes like Babylonian math. They will talk about all those things like who's for example, Limbus is another major contributor major contributor of calculus. A lot of people only knows the Isaac Newton, but Gottfried Leibniz is also very well known. Actually, a lot of time Isaac Newton stole a lot of his work. So they kind of like, I mean, they kind of like look at each other people's idea and they try to reinvent to be a better idea. So Leibniz actually produced something called implicit derivative, where Isaac Newton is more well known for explicit derivative. Okay, so basically add this to per person. So Isaac Newton come out and he says, well, back then all the mathematicians or scientists they all like believe in God. They are very religious. So for example, like says Isaac Newton is very religious. He trying to find he just look at a telescope and he's looking through the stars and he's looking at like how fast the planet is moving. So one day he'll observe like oh it's in this location, and next day he'll use telescope is looking oh it's that different location. So you want to find out how fast is that a planet move. Okay. Well, actually, he was like according to myth, like he's trying to find a the place where the heaven is, um, because he believed there's a heaven because he believed in God. Now, as opposed to nowadays, all the scientists usually are atheists, but back then, a lot of scientists are really religious. Um, and so, like for example, like another religious person will be everybody probably know if you study like European history, like Descartes, right? Descartes is also a very religious person. Do you guys know Descartes? Descartes it says, "I think, therefore I am." Okay. All right. So a lot of things like this, you're gonna start with understand a little bit of history. The history is, back then, according to European history, right? That's actually what I studied. When I studied European history, and they start to talk about science, industrial revolution. But before industrial revolution, there was a lot of scientific discoveries, and including people like heliocentric and geocentric. Do you know what's the difference between heliocentric and geocentric? Sun is in the center, is heliocentric, and geocentric is the Earth is the center. But do you know that who told Pope that it's not geocentric, it's heliocentric? Huh? Galileo. Do you know what happened to him? Well, it's not a house arrest. It's actually, there's a technically term. Do you guys know what a term is? It's essentially house arrest, but there's a term for it. Have you heard about excommunication? Right? He was excommunicated inside a tower, and he's not able to publish any paper so other people can see it, because whatever he published is against the Pope, because Pope says we are the center of the universe. Okay, we are the center of the universe. And Galileo says, no, we are not center of the universe. And he start publishing paper. And everybody is like, no, you cannot say that because that's not what the Pope says. And so it becomes like a very discrepancy between two individuals. So he was locked up in the excommunicated inside a tower. Okay, so unless you guys have more to contribute, then you can add in. Otherwise, let me talk because I got a lot of things to go through. Okay, so that's what happened. Now, let's start with a very well-known problem, which is when he was observing a planet, he discovered that there's a problem that he tried to figure out. And at that time, it's the biggest problem, the biggest math problem at the time, at the 1600s, is known as a tangent line problem. A tangent line problem is a big deal at the time. And they say, okay, well, hey, what is a tangent line problem? So remember the planet I was talking about? So first of all, they thought like a planet is moving in circular way, but then they find out no, it's going on like elliptical path. Okay. So let's just say there's an elliptical path of Saturn. It's like kind of traveling around the sun, and there is a Saturn right here. And so one day you take a screen, like you take a picture or telescope or whatever, and you find out the next day it's going like right here. It's moving, right? So it's moving. So I want to find out. So what Newton says, I'm wondering how fast this planet is moving. And in order to find out the planet is moving, is you have to find slope, right? Slope of the line. But the problem is not slope of a straight line. It's slope of a curvy line. And if you find a slope, then you will find the velocity of this planet. Is that okay? You find the velocity of this planet. So this is known as tangent line problem. This line that's only intersect one point, just like this is my water bottle, and this Apple pencil is a tangent line to this water bottle. So that's only touch a single point. And so if you go into this, you find a tangent line problem. So that's the first problem. The second problem is the area under the curve. So at a time, they have to solve the first one and they have to solve the second one. The tangent line problem, the area under the curve problem. It turns out both are solvable. Especially, that's how Isaac Newton come in play when they invented calculus for it. So originally, it started with those two problems. Okay? So then, how did he solve it? Okay? So it starts with the idea is we have to understand limits. What is the limits? You learned limit last year. Can you tell me what's limit mean to you? What does limit mean to you? That you learned a lot last year. Can somebody tell me? What'd you say? Okay. Okay. That's fair. So I'll give you some analogy. Anybody have very annoying brother at home or annoying sister at home? Gia is your annoying brother sister? Oh, okay. I don't know. But does anybody have an annoying brother or sister like come up to you says, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you. You have that? Bennett? Bennett do that? Sometimes does it. Okay. So basically is a sibling will come up to a person and it will be like, okay, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you. Until somebody gets slapped. Right? And, but you are not the one that started a fight. He's the one that started a fight. You are just infinitely getting closer to that person. And that's the idea of limit. The idea of limit is I'm going to get so close to you and make you feel uncomfortable. And I'm going to slowly approaching to you. Slowly to get to you. Does that make sense? So that's the limit. And we assume that we can get there. Okay, we assume that we can get there. We can get really close to hit Jordan. So that's the limit. So limit is a slowly approaching something. And not only that, is approaching something from both ends. Okay, but we're going to talk about it. So with the limit foundation, the idea of limit was introduced. After limit is introduced, that we able to tackle the problem of tangent line problem. So that becomes the first part of the calculus. The first part of the calculus is derivative or differentiation. The second part of this is called integration. So what does a derivative help you find? What's derivative help you find? Do you guys know? Slope, yeah. So differentiation. So if I were to take a derivative, it will help you find slope or rate of change. Derivative. Integration. Integration is, okay, so derivative will help you find slope and will help you find rate of change, which is, that's very important because rate of change of a planet is how fast the planet is moving. Got it? Okay, integration. And integration, which is also known as the antiderivative. Antiderivative. Antiderivative is the opposite of derivative. But this will lead to solve tangent line problem. And this will lead to solve area under curve problem. Okay. So I'm going to give you an example. I'm going to show you. And this is probably going to be the first time I'm showing. I'm going to show you again when we introduce derivative. So the first problem we'll solve is due to this. Everybody can find the slope of a straight line, right? Slope of straight line, that's no big deal. I can find slope is, we're going to see what is rise over run. I here is going to be 2, I here is 3, so slope is 2 over 3. We can find slope of this line. That's not a big deal, right? So basically, it will find the slope of a non-linear line. So we want to say a non-linear line. Because linear line is very easy. What do you mean by linear line? So for example, I could have a slope of, I can have something like this, and I want to find the slope of this point. Okay, I want to find the slope of this tangent line. Okay, so this is known as a tangent line. Tangent line is only intersect the graph in one point in that region. We're talking about this region. If the graph curve back in here, then it will intersect more than once. But in that region, I only intersect exactly once. So that's known as tangent line. So what Newton proposed is this. Newton says, well, let's establish a couple the arbitrary coordinates. Okay, so this coordinate that we're gonna start to using this coordinate help me find equation tangent line. And let's start with this one. So this is a tangent line problem, and so we was able to solve use of basic ideas. And this basic idea is some graph like this. Actually, I make more steep. Like this, doesn't matter. You can grab anything. So I want to know that this line here, this black line here, which is known as a tangent line. And this is f of functions. Is that okay? Am I going too fast? Okay, tangent line is only intersect one point. So what we're gonna do is we're gonna create another point here. So we're gonna name this is the x, right? This is the x. So this coordinate is gonna call what? What is this coordinate? What will be the arbitrary coordinate of this point? Nope. What'd you say? Almost. A coordinate in coordinate form. X what? X comma f of x, right? X comma f of x. So that's the first point. Now what Newton proposed is, hey, let's use something called secant line. And you're like, what the heck is secant line? Secant line, instead of intersect the water bottle like this, but it's intersect the water bottle like this. So it's connect 2 points of the circles, okay? That's called a secant line. A secant line is start with, I'm gonna create a point right here, and I am gonna generate a slope of this slope, the line of this slope. So the slope of this point is called a secant. So the blue line is called a secant line. It intersect more than 1 point. So it's 2 points here in this small region. Okay? And this point that we're gonna have at this distance here, this distance from here to here, we're gonna say is h. Some type of h that we want to find out the distance of. The h could be 10, could be 1, could be 0.5, but usually it's smaller value. So we're gonna say it's h. So if this is the h, what will be the x coordinate here? What will be the x coordinate? X plus h, yeah. And what will be this point here? The coordinate is going to be what? What's the coordinate of this new coordinate? Of x plus h, right? Oh, so now we have a 2 point. With 2 points, we can find the slope of this 2 point. And we're going to say slope of secant line is equal to y2 minus y1 over x2 minus x1. That's why we're doing that packet. We give you 2 coordinate. That's why we give you a test question. We give you 2 coordinate. Ask you to find the equation of the line. So this secant line has slope And the slope is based on those 2 points. So we're going to use y2 is going to be f of x plus h. Is that okay? Zooming where? I can't really zoom in. Okay. So x plus h minus f of x, which is the red point. It's a red point, is f of x. Is that okay? Over x plus h, which is the blue point, and minus x. Minus x. Is that okay? Now, what happened on the bottom? They cancel, right? So that's going to be f of x plus h minus f of x over h. And this becomes a very well known as called difference of a quotient. Difference of a quotient. You don't need to know the name, but in pre-calc we call it difference of quotient. I never got a chance to teach this because it's not an AP exam. So the difference of a quotient, then we say, okay, well, we're gonna do a tangent line. So now we're gonna propose this idea of tangent. The tangent is equal to a limit as h becomes 0. H slowly becomes 0. It starts with maybe like 0.5 to 0.4 to 0.3 and 0.2 and 0.1, 0.01, 0.001. So it's approaching to 0. So that's going to be x plus h minus f of x over h. So what happened when h approaches 0? So let's just say here is the h, and we say that here is like 0.5 units. What if it's reducing from 0.5 to 0.4? What will happen? The slope is going to be increasing or decreasing? What do you think? According to this graph, slope is going to be decreasing or increasing? It's actually going to decrease. So let's just say if I have another point, we say this point here, and we're going to have this, right? It's not as steep as before, right? And we're going to say this point is going to be here, and it's going to be here. It's almost a tangent line, but it's not really close. But as I'm getting closer, it will become the black line. It will become the black line. So when you get very, very close, it will become the black slope. Now realize the h is on the bottom. If the h on the bottom, when it becomes 0, what will happen to the function? It will be what? Undefined. So we have to use the idea of limits. We can get so close to it, but not close enough to make it undefined. Okay, not close to make it undefined. So what we're gonna do is we're gonna produce this, and this doesn't do you justice. Or actually, you can use the decimals. So get your decimals out, and either on computer or whatever. Okay, so you can open the folder on the top. Do you see this folder? Do you see the folder here? And do you see the example? And then you're gonna scroll all the way down. Folder, example, and into secant line and tangent line right here. Okay? And let's just say today, I want to find the slope of this this green dot. Let me change your function. Let me change it. Let's say e to the x. Let me change e to the x, which is you go to example, folder, example, and scroll down to secant to tangent line. Okay. And what happened is, do you see that I have, I'm going to start with this point. Oops. So I'm going to start with this point here. Okay, so what happened is this red dot is going to get closer, right? Oops. Until you see here, it's very close to become a tangent, right? Very, very, very close. We're going to get so close to it, but it's undefined at this point. Do you see the tangent line is the orange line? But before that, there is a purple, right? But purple, when you get it so close to it, you're going to get to here, and that's the blue line. But when the calculation, it will end up to be undefined. Why is undefined? Because h has become 0. If h becomes 0, the bottom is equal to 0. You cannot divide it by 0. Therefore, it's undefined. You can try it with any function. You can do it with x squared if you want to. You can do x squared like this. And we say we want to find slope of at 1. At 1 this point, right here, at 1. That's what we're trying to do. But when we get there, it's undefined. So we need to rely on the idea of limits. What's the idea of limits, right? So for example, that's a limit. So anyway, so this is a tangent line problem. Newton discovered this and he solved it using this idea. And later on, we're going to know this is known as a definition of derivative. Later on, we're going to talk about it. This is equal to f prime of x. That's the definition of derivative. Now let's propose a second problem. Second problem is, hey, can I find the area here? Is it possible for me to find area here? Is it possible? Of this graph of this? Yeah, it's just a trapezoid, right? Can we find the area of trapezoid? Use trapezoid formula. By the way, you should know the trapezoid formula, but I know most of you guys still forget. It's b1 plus b2 divided by 2 times height. Okay, so trapezoid. Later on, we're going to learn something called trapezoid rule. Guess what? You have to memorize then, as opposed to now. So you don't have to know it right now, but you can find the area of trapezoid. Now, the problem is, hey, I can find a straight line. What if a line is not straight, right? How do I find area here? This line is no longer straight. And that becomes a second problem. Area under the curve. How do we figure out area under the curve? So we start with the most historic way. I don't know if you remember back in the day, I think physical science probably give you like, or a math class, they give you a map, and the map has a square inside, and you count how many square inside to count how many square miles. Have you done that before? Mm-hmm. Yeah. Like you just count, you just physically count. It's not even math. You just count how many square inside this island. And you can say, oh, this is estimated to be like 52 square mile, right? Because it's a 52 square. So what happened is here, we're going to click on folder, and we're going to go to example again, and we're going to go to something called Riemann sum. Actually, I don't like this one. So I'm going to use the one I saved. So the one I saved is slightly better. It's like here. Okay. So we want to find this area under the curve, but we can start with, I say, it's 4 rectangles. And we're going to do this. No, we're not going to do trapezoid. We're going to do something like left endpoints. Is this an accurate estimation of the area? No, because there was a lot of overlap. There was a lot of undercounting part. But we can say, well, we can calculate this. We can go into this function, 1. And we can plug in 1 to this function. We got 1. So we know 1 times 1 is 1. So we can find the first rectangle is 1. And the second one, we're going to go here. And we'll plug in to 1. From 1 to 1.75, the base is 0.75. Times of 1 is 1. So it'll be 1 times 0.75 is 0.75. The first one, second one would be from 1.75 to 2.5 is 0.75. 0.75 times 2.17 is going to get a value. So we find the second rectangle. So we can do that, keep on going. However, we says, how do we make this estimation more accurate? How? How do I make this estimation more accurate? Somebody say out there, say it out loud. More rectangles. Yeah, just fit more rectangle. Make the width smaller and let's fit more rectangle. And we'll see that if n equal to 4, do you see that? It's a more accurate representation now. And as I'm keep on going, I'm getting better. As I'm keep on going, I'm getting better. And that matter of fact, I said 20 rectangles is not enough. Let's go to 1,000. Oops, my bad. Let's go to 1,000. Right? And 1,000, let's go to it. Okay, so 988. Right? Is this accurate? Do you think this is accurate? Well, let's zoom in to see it. Ooh, still have some type of error. So what the Riemann is another mathematician come in and says, we not only can do a partition, we can break down to infinite partitions. So if a partition is so small, the error becomes negligible. The error becomes negligible. Okay, so the so small that there's no more area like this opening space anymore because so tiny. It's like you line up all the hair and just calculate all the hairs, and you're not gonna see even small edge. You're still gonna find, but we're gonna do it smaller than hair. Okay. So that solved the second problem, which is we know is the area under the curve. So we figure out that we solved both problems. So Newton's and Riemann and Lembitz, all three mathematicians, and maybe many other that I don't know about. For example, El Hutto. For example, I don't know. There's a lot of mathematicians back then. We cannot name. Lagrange. That's another one. Lagrange. That's his name. Okay. So far, do you understand the introduction? If somebody asks you, what is calculus? Okay, I remember I was in a ping pong competition, and this Indian lady come up to you. He's like, "Hey, I like you." I was like, "I don't know you," and she's like, "What do you do?" I said, "I'm a math teacher." He's like, "Well, teach me about math." I'm like, "Okay." It's like, "What class you teach?" It's like calculus, and so I sit down with her. I explain to her what a derivative is, what the integration is, and I explain to her all the things. So you got to be able to explain like a 3-year-old asking a question. Why is this useful? How is it used? Okay. By the way, I didn't know polar coordinate we learned last year is useful until 2 weeks ago. You know how robotic arm, like to grab stuff, That's a polar coordinate. They use polar coordinate because it's going by angle and how far they have to stretch. And they actually use polar angle because I didn't know that until I saw Mark Ruber's video. Because my son got a Mark Ruber hack box. Anybody got a hack box before? It's kind of fun to build a hack box. And there was a hack box video, and he was talking about, yeah, this is how they find things. Polar video, like you see the machine like grabbing, sorting stuff, and they just go in here, grab, and that means there's angle here, this angle from here to here is 60 degrees, and how far they have to go. That's a polar coordinate. They use a polar coordinate to do the robotic. Which is, I didn't know that. I was like, polar coordinate is so useless. I remember saying that last year, right? And it was like, shit, it's not useless. It's actually useful. Anyway, sorry, I get excited. All right, now, the next thing is, why do we do limits? So what is limits? For example, limit x approach to 1 at x cubed minus 1 over x minus 1. So assume this ping pong paddle is a black hole. As a black hole, okay? And this black hole located right here. Located right here, okay? And I want to find the location of that black hole. Okay? Is any volunteer want to come up? Join me. Yeah, Bracken, come on. I like white people. Okay, you can stand on that side. Okay, so today we want to find this black hole. We want to find out the coordinate of this black hole. But the bad idea is me standing on top of the black hole, right? Because I'm going to die like 18 different ways. Either slow death or fast death. I don't know which one is it. Spaghettification. Yeah. Wait, the time's already up? Okay. Okay, so basically, we want to find this location black hole, but I can take a GPS, like take my iPhone and find the longitude and longitude. I can slowly approach it. But if I'm slowly approaching, if I'm just only from one perspective, it's not very accurate. So the best thing is the limits is you have to approaching from both ends, and that's gonna be a key memorization. You have to come in from both ends. So what we're gonna do is we're gonna take one step forward, getting closer from this side, and we're gonna look at our GPS, and we're gonna make sure we're not dying. Okay, unless you watch it like Interstellar. Haven't you seen Interstellar? That's such a good movie. Yeah, you go into a totally different dimension if you go to black hole. But we don't know. We assume that we're gonna die horribly. Okay, we don't want to stand on top of that. And me and Bracken's gonna take another step forward, and we're gonna take another step forward. We're gonna slowly approach, just like I did to Jordan. I'm not touching it. I'm not touching it. I'm not touching it because I don't want to touch the black hole. I don't want to die on a black hole. So, but we can get slowly because we can see. Well, let's get closer, right? Let's get closer. Now, I don't really want to get too close to him because he's not my type. I like white people. I don't like it that way. So we can get so close to it, and we can say, okay, well, on this side, I got coordinate of 1.9, and he says, well, the coordinate I got is 2.1. And we can get closer, maybe 2.01, and maybe this side is 1.9. And that's how we find this black hole. And this black hole happened in a function, believe it or not. So I'm going to show you. Thank you, Brad. Okay, so this black hole did happen. If you look up the equation, you say, hey, I'm going to type in the decimals here. We're going to type in the decimals here. We're going to put new graph. We're going to say x cubed minus 1 divided by x minus 1. And looks like this. It looks like, hey, it's a very innocent graph, right? Nothing happened, nothing strange. It looks like parabola. And you're like, wait, why is it parabola? I have x cubed minus 1 over x minus 1. Why is that parabola? Do you guys know why that parabola is? Why is that parabola? What'd you say? Ah, good. Factoring. You're factoring sum and difference of the cube, right? And then you can simplify. But right now, we assume we don't know that. That's called how to find the limit algebraically. Right now, we're not going to find algebraically. We're going to find it numerically. So what we're going to do is we're going to click on the wheel right here, which is today's homework is fairly easy. You just click on the wheel, and you type in this. And obviously, if you go to 1, it says undefined. Wait, why is this undefined at 1? If you go to here, this hole, and you say, let's go to 1. Wait, there's a hole. So, well, it's not tangent line. We're not having fun tangent line. We're just trying to find out the hole right here. We're going to find out the location of this hole. How do we find a location of this hole? Right now, using limit. So what we're going to do is, today's homework is actually fairly easy. I want to approach 1 because I know 1 is going to cause bottom undefined. Is that okay? So if I go into 1, then we say, okay, 0. We're going to approach. So according, I'm from the left side. Brackets from the right side. I'm approaching from 0.9. And we're going to say approaching closer and closer and closer. So we come up with 2.9997. Okay, but and you guys should try this because that way you know how to do your homework. You should be able to. You basically record down all this data today using Desmos, and you're gonna approach this. You're gonna say, okay, well, 0.0001 and 0.001 and 0.001 and 0.01 and 0.1. And you see that the value is going toward what? Oh, I mean, it's not 0.1, sorry, it's a 1.001. 301. So what is the value approaching? What is approaching? It's approaching 3 because Bracken's coming from one side, Mr. A is coming from the other side. We don't want to stop in black hole, but we're gonna approach both sides. We're gonna say both sides so many times. Limits always approaching from both sides, unless you do one side limit. But limits always approach both sides. If we don't have anything, we always approach both sides. We see what happened there. Is that okay? We see what happened. So that way we know what is that limit is equal to. So today's homework, basically you just plug in data using calculator. You're gonna figure out what it reached to. No, what it reached to if I reach that value, because we cannot do it mathematically. Let me show you how to do it mathematically though. Mathematically, so this is called numerical approach. Numerical approach. Now, if I want to do an algebraic approach, I'm going to do what Yara says. It's going to be x minus 1 over x minus 1. This one's going to be x squared plus x plus 1. And if I cancel this, if I reach 1, because the plug-in, 1 squared plus 1 is equal to 3. And that's how Yara says we can actually cancel factor. But that's going to be the first method we're going to do. We're going to introduce you more things tomorrow. But thanks for listening. See you next time. Plug in 1. Before I cannot plug in 1. Now I can plug in 1 because 1 x minus 1 is cancel. Bye. Yeah, today's homework is fairly easy. I'm just giving you a big over scope of everything, and today's homework is easy homework. Hi. Oh, you did. I have no problem if you did.
Yesterday, I think my test was.
Huh?
Yesterday, my test was.
Oh, yesterday? We teach you that last year. You should get everything.
I didn't know like testing. I know the user thing, but I didn't know.
Okay.
I didn't review it.
Yeah, that one you did. Yeah, you showed me already.
Might be supposed to do like this on my mother day. I have like 2 makeup tests.
Well, you should have come yesterday. Where were you yesterday?
So I don't like.
What?
I don't like.
I don't have time either. I don't have time for you.
Oh, what are you?
You're leaving probably 3:40.
Okay. No, I'll try to.
I haven't
Because
finished.
right now I'm at C.
Huh?
Because right now I'm at C.
Right now it's a. Yeah, the Alex test one looks pretty gross.
Because that is so much better than my quiz was for Alpha.
Alex, what happened to the trick test? I saw the score. I'm like, what happened?
I don't know. I just went down.
I'll put it in right now. That's the
Right now. I might be able to. What did you get? What?
Who is Kyle? Kyle Lin, of all people? Wait, Miss Jones? Miss Jones or Miss Hack? She's nice.
What's up, Michelle?
She's really nice though. She's really sweet. Why? She's so sweet. She's like the sweetest person. Arthritis.
Huh?
The person invented calculus.
Oh, okay.
We talked about it last week.
Yeah, I have some secret information. I hear that Trey like half-assed his work last night, so like you should go check it.
Trey half-ass.
Yeah, that's.
He's always half-ass everything. I don't even need to be there to know like he half-ass. He half-assed yesterday's homework.
What's it called? In like seriously like going like what things this guy says he like I half-assed my words. Can you just show it to me?
Trey.